Hello, everyone. I'm Carlos Timoteo. I am machine learning engineer at Pythian. I'm based in Ottawa, Canada, and I'm here to talk to you about scaling your TFX training pipelines using TPU pods. So let's get started. The idea behind using TFX is pretty much adopting the best practice from software engineering and putting them together with the best machine learning development practices. So in other words, what we want to accomplish when we use TFX is leverage all the best practices into putting our machine learning systems into production. I won't be extending too much my talk into describing TFX or even contextualizing it. And by that reason, I assume you already know TFX. When we write a machine learning solution, we have several concerns and issues that we need to deal with. On the left-hand side, we have coding issues, and on the right-hand side, we have machine learning issues in scale. So what's important to take from this information is that when we are implementing our machine learning solution, besides having code concerns and challenges, we also have data challenges. For example, we need to perform data validation, we need to perform our model evaluation, and at the same time, we also need to understand how fair our model is. At this talk, I won't be extending too much on discussing TFX, as I was saying. Therefore, what is important for us to understand is that TFX is a flexible end-to-end machine learning platform, and it contains all the best practices. It implements libraries from the TensorFlow ecosystems, and it is very easy to implement and to extend your pipeline by plugging components into it. Another interesting information is that TFX is ready for Evolve and to support multiple platforms, like when you are trying to deploy your model into an edge device, you can use TFX pipeline to do that work for you as well. Here's an example of a TFX pipeline. This pipeline is implemented in Airflow runtime, as we can see, and all the components are depicted in orange. We start from the left. So we have our first component called the example gen. Next, we have a statistics gen, following by example validator, schema gen, the transform, trainer, evaluator, and pusher. As we can see here, we can push our model, our trained model in this situation from many endpoints like TensorFlow JS systems, TensorFlow Lite platform, TensorFlow serving. At the same time, we can also use our pipeline and implement a inference pipeline, in this case, a batch inference pipeline, which is quite small, but it reuses some of the components that you have implemented on the training, so it can run the inference for you and save it in the proper location. Usually there are three ways to run your TFX pipeline. It's very common. You find talks and guides and tutorials explain you how to run a TFX pipeline interactively in a notebook, for example, using Google Colab, or in your laptop using Jupyter Lab. But not as much. We'll find some tutorials explaining you how to use and to run your TFX pipeline on the cloud, although we have a very rich documentation for the AI platform, but it's still not very complete. When we put together AI platform and TFX, There is a new product, a new offering actually, that is born from this conjunction, which is our AI platform pipelines. AI platform pipelines implements Kubeflow pipelines. And on top of Kubeflow pipelines, we can implement and deploy TFX pipelines. We understand how that works in a bit. So our traditional machine learning training pipeline at GCP becomes more or less what we have on the top of this slide. For training, we can have data residing on BigQuery, where we process the data using BigQuery or Dataflow. Also, we can extend some of the TensorFlow components by using TFT. Next, we host our pre-processed data into a GCS bucket, and then we run our training routine on AI platform jobs, implementing a code using TensorFlow that will be able to load the model. We'll be able to load the data and run the training job for us. When our TensorFlow model is trained, it can be passed to GCS, so it can be ready to be deployed for serving reasons. AI platform pipelines is a collection of several SDKs, libraries, components deployed on top of GKE, Google Kubernetes Engine. As we can see here in this picture, this is the architecture design, a high-level architecture design. We can see all the components that we use. We have our TFX pipeline templates, which are library functions that we can reuse. We have our SDK. We have also the Kubeflow pipelines SDK, where the TFX SDK is implemented and extended it. We also have custom components, pre-built components, and we can use notebooks. In AI platform pipelines, we don't have native notebooks implementation, although for that we use AI platform notebooks, which is outside of the GKE cluster. What's also interesting to see here is that our Kubeflow pipelines implements a Argo workflow engine, where your multiple steps, which represents your pipeline, can be implemented and run in multiple work engines. For example, Dataflow, AI platform training, and BigQuery. We also have a metadata store. Natively, you have an option to use a metadata store inside GKE, but you also are free to use your metadata store on Cloud SQL or any other MySQL implementation. You just need to provide the proper credentials to it. Then comes the question, but how can I experiment fast? Sometimes we have our use case, we have a lot of data, we have a complex model, and it's just too hard to experiment fast. Well, the traditional approach, and the very straightforward one, is to implement GPUs and TPUs. Okay, that becomes easy since we have access to GPU and TPUs from our notebooks. But what about using GPUs and TPUs on our final machine learning pipeline? How can we implement these in an easy way? As we all know, GPUs and TPUs are very used just because they provide more computing power and then alleviates your pre-processing and model training bottlenecks. Okay, let's give a try on GPU first. Nowadays, on TensorFlow, we are only allowed to use two distribution strategies to work on. One is our mirror strategy, The other one is the TPU strategy. Other strategies are being supported slowly and slowly as soon as we have new versions being deployed. In this situation, we have our model code being replicated for every single core that we are using. So in other words, you are splitting the data to be trained by the same exact copy of the model in another GPU device that will be able to do half of the work each. In this situation, like we can see, we have 2 devices, so we can split the work effort in half. And with the time, there is a communication between those devices where all the gradients are being adjusted. Okay, we just saw how it works to distribute our computing by splitting the data. But how can I split the data depending on my distributing strategy? Well, one way you can do it, and this is a TFX sample code, is to use your distributed strategy and implement and you call this function experimental distribute dataset, which is responsible for collecting your TF dataset and distributing it through all the cores that are available, through all the devices available. As we can see here, the Pythian function, where we process the data, where we ingest the data from TF records and load into memory, is being wrapped by experimental method called make batched features dataset, where I have all my rules regarding shuffling and parallel interleaving and dropping the final batches if they are not complete. You can check the documentation to see more how it works in detail. One important note is that using experimental distributed dataset, it's only available for TensorFlow 2.3. And for that, you only have those 2 distributed strategies working, mirror strategy and TPU strategy. Another alternative that we have is if you have very expensive preprocessing computations, you can perform a snapshot and alleviate a little bit of this effort. And if you really have just too much data, you can also use a service cluster to provide this data via gRPC. And that's how it works with the distributed transformation. Since it's a new feature, we are not covering those 2 features here in this presentation. And then you may think, okay, but I don't have enough resources. I have this code, I know what to do, I run on my notebook, but even though it just takes too long, I don't have everything I need to do. Well, and then it comes your AI platform jobs. Using AI platform jobs, you're able to train models without managing infrastructure. I like to say that you request your cluster configuration, all the resources you need on demand, and after a couple of minutes, you have this infrastructure allocated for you and ready to be used to run your job. AI platform jobs are also a nice way, an interesting way to use GPUs and TPUs. And then how it works. How would be my Docker journey if I want to run a customized container and run my customized training job? Well, first you would need to develop your TensorFlow model with your training routine. Next, you create your Docker file. You build the image, you register it into container registry, in this case, Google Container Registry, and then you submit your job. by providing the proper container name and tag. As we can see here, our code is very similar to what we have on our notebook, except we're gonna have extra parameters that we have to deal with. You can see more code samples on the repository. Here's an example of how you can extend your Docker image on top of a pre-existing DLVM image. DLVM stands for Dense Deep Learning Virtual Machine. Well, after you run your just build image locally, you are able to provide the arguments and test how it goes, and then you can finally push to GCR. To submit your training jobs, it's very easy. Now you just need to provide the proper image URI when you're working with your masters, and also you can provide the same URI when working with multiple workers. If you need to provide extra configuration or arguments, you can use configure YAML to provide this information, and also it can be used for hyperparameter tuning. When you submit your job, you just need to add the -- config flag. Having a look on how it presents to you after you submit your job, you're gonna see in your AI platform jobs interface the list of all the jobs you have submitted, and also logs and other information like the approximate consumed machine learning units that can be easily converted to understand the costs. Then you can say, okay, so far we haven't learned yet how to run GPUs or TPUs in my final production pipeline using TFX. I need TPUs. I still need TPUs. How can I do? Well, the traditional approach that you can see in several documentations and tutorials is to work with Google Cloud TPUs. It's an easy way to train and run your machine learning model training using TPU, and you have total control of the instance. The steps to use Cloud TPU: first, you need to set up all the prerequisites, enabling API access to also your GCS bucket storage. Next, you create your nodes. And then from your notebook code, you connect to the TPU and submit your job to run on the Cloud TPU. This is an example on how to use by invoking gcloud commands. The first command, we are creating our notebook server. Next, we create our Cloud TPU. As you can see here, our accelerator type is Cloud TPU V2, and you can change that for V3 if you wish. In your training code, this is the change that you need to implement to use the proper distribution strategy when you are able to connect to your TPU cluster. Have in mind that your TPU node IP address will be provided for you just after you create your TPU cluster. Okay, but how can I use GPUs and TPUs on my TFX pipelines? I learned how to use on notebooks, but I still have no idea on how to use on TFX pipelines. Well, first, you're gonna need to modify a little bit your TFX Docker container image by installing CUDA, NCCL, CUDN, and also your preferred TensorFlow version. As we can see here, we are extending our TensorFlow TFX 0.240 version, installing all the required packages so it can use GPUs and communicate with the GPU cards. And also I'm installing my preferred TensorFlow version. By the end, you can see where there is a pip install -- upgrade TensorFlow equals 2.30. Also, in this situation now, we have to work with configurations, and we are providing our custom configuration. As you can see, I'm specifying my accelerator configuration. I'm setting the count for 4. So in this case, I will have 4 cards of NVIDIA TELUS P100 cards. Also, it's important to notice that you have to provide your image URI, the one that you specify, when you run the Docker build command on the Docker receipt that we just saw. And then in my notebook code, I have to change it a little bit to prepare it to submit for TFX. In this case, if I want to use GPUs, the only provided way is using mirror strategy. For that, I will set my mirror strategy object. I will create a scope, and I need to compile my model. Next, I just need to call fit, and then my training starts. What about TPUs? Well, it's not very different from that, except that you don't need anymore to configure any Docker image. As we can see here, we have a master worker and a worker type where we can define our Cloud TPU cluster. As we can see here, we are using TPU v3. We can easily change it for TPU v2. And we still need to provide our preferred TensorFlow version and to specify my image URI that will be used to run my container. And here's the sweet spot. I couldn't find easily documentation that specifies how you can connect your AI platform jobs into your Cloud TPU that's being created by that configuration using AI platform jobs. And the sweet spot, the most important intake that I want to give you, to provide you, is exactly for you to use something like I'm using right here. All the information regarding your TPUs, the zone, the project name, will be stored into your TPU config. This is an environment variable that is allocated as soon as AI platform jobs creates the required infrastructure for you to use, and when it knows that it's ready for you to connect and initialize. Next, you just need to use your resolver object and connect to the cluster and initialize your TPU system. Don't forget to use your TPU strategy, because if not, you should be using your CPU for training. When you run your model compile, you are submitting your TensorFlow graph via gRPC to the TPU cluster. And when you call fit, there is also another gRPC call requesting your TPU cluster to run the model training for you. In this situation, you can also use, as I showed before, your TF dataset distributed and provide it to the fit. It will happen the same way. All the data will be sent off to the cluster. And voila, now you are ready to go. Now you are able to use GCP, AI platform jobs more specifically, to train your job and to validate your just pre-trained job and push it to AI platform predict if you wish. We come to the end. I hope you enjoyed this presentation. If you have any doubts, don't forget to reach out to me, and thank you so much.